This is the next question on single slit diffraction pattern, something that we saw in the last video. So this is the next question. The question says a monochromatic light beam is incident on a single slit of width 0.8 millimeter and the diffraction pattern and the corresponding diffraction pattern is formed at a screen which is 0.8 meter away from the slit. The second order bright fringe is at a distance 1.6 millimeter from the center of the central maximum. The question asks, what is the wavelength of the incident light? Of the incident light beam. So we saw in the previous video the setup for a single slit diffraction pattern right here. So let us draw it again. So we have a slit, single slit, which is illuminated by plane wave. Then we have a screen. This is the central part, and then on the screen we see a diffraction pattern. Like so. So this is the slit having certain width b, and this is the distance between the screen and the slit. This is the center. So let us now solve the question. So for minimum, we saw in the previous video that minimum is obtained when b sine theta is equal to m lambda. Sine theta, theta is the angle, this angle up to a point P, So we have condition for minimum. B is the slit width. Now in the small angle approximation, we have sine theta is approximately equal to theta, which is approximately equal to tan theta for small angle. So this gives us, let us call this distance y m for dark. So then this gives us ym for dark divided by d is equal to m lambda. So position of the dark fringe, of the mth order dark fringe, is as follows. Now bright fringe we saw was obtained by solving a certain transcendental equation. So maximum intensity was obtained by solving this transcendental equation, but roughly we can assume under certain approximations that this is roughly in between two successive minima. So if we look at this diagram over here, this is going to be our second order bright fringe, this fringe over here, and this maximum point, second order maximum. Maybe I could redraw it again. So let me choose a different color. So this is the second order maximum. This is the central one, this is the first order, this is the second order, and on this side of the screen also we will have the second order maximum over here. So this second order maximum is roughly in between these two minima. So roughly between second and third minima. So this right here is second minima, this here is third minima, and this green point is second maxima. So we have second order maximum is approximately in the middle of So second order maximum is approximately in the middle of the second and third order minima. So the position of the second order bright is approximately, I should write approximately, halfway between second and third order minimum. So approximately like this. So we can put it from here. We have this expression for minimum. We can put it over here to get so this gives us the wavelength of light is as follows. And we are given the values of all of these terms right here. So this is 0.8 millimeter is the slit width. Position of the second order bright fringe is 1.6 millimeter, and distance between slit and screen is also given to us. This is 0.8 meter. So this comes out to be, plugging these values in the calculator, so our wavelength is 640 nanometers. This solves the question, which was this question was based on single slit diffraction pattern, wherein the minimum is located according to this equation, and maximum is taken approximately between two successive minima. So this solves the question.